Today we're going to talk about metallic bonds. Okay. Metallic bonds are obviously made from metals. That's probably the most obvious part of this, but we think about metals on the periodic table. What kind of ion does a metal form? If we look back at our on our cheat sheet, we can see the metals are all over here. Are these all cations or anions? Well, I see positive, 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 positive. These are all positive. So these are all positive, and cations are positive because cats have paws. So we know that metals form cations. So we really got to keep that word in our brains, like the forefront of our minds. They form cations. Now you might be saying, wait a second, we already talked about ionic bonds. Yes, we did. But metallic bonds need these cations in order to work. Metallic bonds are called the electron C model. Now, stop for a second. Let's use our normal people brains, not our chemistry brains. What do you think of when you think of the word C? You might think of the ocean. You might think of a current. Is the sea ever still? No, the sea is always moving. And so you want to keep that in your head as we kind of begin to talk about these metallic bonds. And why is it called an electron C model? Well, we know that metals form cations. We also know that metals are solids. Most of them, they're solids. We can say that. And so what happens with solids is we know that atoms kind of stay in one fixed position. They kind of move around a little bit. They jiggle, they move. But for the most part, the atoms themselves stay put in a solid. Well, that's not a C. That's not moving. But what has happened with cations? Have they lost or gained electrons? They have lost electrons. So all of these lost electrons are floating around everywhere. So this electron here gets lost and goes around this atom, and then this atom, and then this one. This electron from this atom might go around this atom, and another one, and another one, and another. And it just kind of keeps going that way. Electrons flying all around all these atoms, all over the place. They don't stick to any one thing. They're attracted, those electrons are attracted to the cations, but they don't stay around one. They'll continue around all of them in the whole metal structure. So why is it called a C model? The electrons are moving around all the cations, the metal ions. So for our purposes here, we had all the same cations. They were all red. So all the same metal. That's fine. That's a pure metal. This pure metal here would be really easy to slice a straight line, because of its repeating metallic structure. It would also be easy to bend or move, malleable, ductile, those kinds of things. So if I hit it with a hammer, all of these atoms are going to shift over here. And when they shift over here, the electrons are still going to fly all around them and keep them connected. So this electron C, electrons act like a glue to keep the metal together. That's not how you spell metal. To keep the metal together. Alright. We know that metals are a good conductor of electricity, right? Why? Why are they a good conductor of electricity? Because the electrons are all moving everywhere. If I have an electrical outlet, okay, this is a very silly looking electrical outlet. If I have an electrical outlet and I have a wire coming from that electrical outlet into the metal, that causes a flow. So then, just like a herd of electrons, all of the electrons start going the same direction. All of the electrons start going the same direction. So, electricity is electrons flowing, just like a sea, flowing in the same direction. So whenever there's an electrical current passed through this, the electrons aren't going all crazy everywhere. When there's an electrical current passed through, the electrons all go the same direction. Wherever they're going to go. Maybe to your cell phone, to your lamp, to your whatever. Thumbs up if that makes sense. Okay. Alright. Cool. And so the other thing we need to talk about today is alloys. Does anybody know what an alloy is? Nope. Okay. Alloys are mixtures of metals. You need to think about that word for just a second. Mixtures are not chemically bonded. But we're talking about them with a metallic bond. Why? What? Well, let's think about what an alloy is. And why would we have an alloy? Alloys are stronger. So you can take apart an alloy if you melt it down, but it still counts as a metallic bond, because if I have, we'll just call them red and orange for right now. If I have red cations and orange cations, so they're different, they're still metals, then the electrons can still flow all around them. Now, we saw this when we watched the episode of Hunting the Elements on the bell, the brass bell. So you put different metals together, and it's going to give a stronger property. It causes the metal to bounce back when you hit it so that it doesn't make a dent in the metal. Let's name these things. This is called substitutional. Okay, so you can see that they take the place of the other. So we have that same structure, that same lattice structure, repeating pattern. Just the orange one took the place of the red one. There's one other kind that we need to talk about. Interstitial. So interstitial is a little bit different than substitutional in that the basic pattern of the majority element is not interrupted. But there are other elements. A lot of times they're a different sized atom, perhaps, in between. And what that does is it causes it to be harder for this metal to bend. It gives a lot of strength because you're stopping it. It's like putting a chalk behind a tire. You can't move this tire. You can't move this atom, sorry, because this little atom is in the way. We still have electrons. We still have those electrons flying all around all of the things. All of these ions in here. The electrons are still attracted to those cations. It's just that because of the placement of these other elements, we get a stronger material. Okay, I didn't hear what you said, Brendan. Yeah, there's orange is cations and red. So you have red and orange. It's just in the interstitial. You can see those orange ones are a lot smaller. And we'll talk about that. Like an example is is carbon steel of that one. And you'll see that in your thinktivity in a little bit. Okay, thank you. Alright, so some examples. For instance, the Bronze Age. How did the Bronze Age change the world? Stronger weapons. Right? Better tools. Bronze is an alloy. Bronze is 75% copper and 25% tin. That is a terrible copper, so we'll write it out here. Copper and tin. Notice, this is not a ratio like with a subscript. I don't have copper 4 or tin 2. It's a percentage because alloys are mixtures. Okay? Because alloys are mixtures, we mix in 75% copper to 25% tin. How many of you might play a brass instrument in band or know what a brass instrument is? Okay, so brass, different things we make of brass, is 70% copper, and 30% zinc. Make it so shiny. Carbon steel, like what we build buildings with, and we talked about the interstitial. Carbon steel is an example of interstitial. It's iron, and that's stainless, sorry. It's 99% iron and 1% carbon. So that carbon causes the iron to be much stronger. And then last example that I'll give you, stainless steel. So like we have stainless steel appliances, we have stainless steel, lots of stuff. And it is 18% chromium, 8% nickel, so that's why it's not very corrosive, and the rest is iron. So it's still steel, but steel indicates an iron mixture. But that chromium and the nickel is what gives it that shiny, non-corrosive surface. So you can see that you change the properties a little, but you can still take them apart through some processes. Okay.